In the next two videos, we'll look at linearization. Linearization is the process of turning a curve into a linear equation. The College Board, who writes the AP exams, defines linearization as approximating a value on a curve using the equation of a tangent line. The equation of a tangent line is not a new concept. This is something that we've been doing since Unit 1. In linearization, we're just using the equation of a tangent line in a slightly different way than you have before. In this video, we'll look at what linearization is and how to find the linearization of a line. And then in the next video, we'll look at applications of linearization. That is, we'll use the linearization to approximate a value near a point. The idea behind linearization is that most curves will appear linear if we observe them on a small enough scale. Let's look at a few examples of that. Take a moment and try to figure out what the equation of this line looks like. This line appears to be linear. It has a y-intercept of 0, and the slope appears to be 1 over 1. So this graph looks like the equation y is equal to x. What about this blue line? It does appear to be linear. It passes through the origin, so the y-intercept is 0. This one has a negative slope, and the slope appears to be negative 1 over 1. So this equation looks like y is equal to negative x. Finally, we have this green line, which appears to be horizontal. The origin is up here. If we count down from the origin, negative 1, negative 2, negative 3, negative 4, negative 5, the green line appears to pass through y equals negative 5. That would be the y-intercept. Since it's horizontal, the slope is 0. So this line looks like the equation y is equal to negative 5. In these three examples, the actual scale of these lines is hidden to us. But keep in mind that most curves could appear to be linear if they're observed on a small enough scale. Let's have a look to see what these red, blue, and green lines really are. This red line appears to be straight. If we turn on the axis numbers for the grid, we can see that we're actually zoomed in really close. So what happens if we start to zoom out? As we zoom out, this straight red line starts to look more and more curved. And if we zoom out far enough, we'll be able to see the shape of the full curve. And from here, we can tell that this curve is actually sinusoidal. The equation of this red curve is actually y equals sine of x. Here is the blue curve, which looks like the linear equation y equals negative x. If we turn on the axis numbers, we can see that we're actually zoomed in really close. As we zoom out, this blue line starts to take on more of a curve. And if we zoom out far enough, we'll be able to see the full shape of this curve. The equation of this blue curve is actually y equals x cubed minus x. Finally, we have this green line that looked like the equation of y equals negative 5. Turning on the axis numbers, we can actually see that this green line passes through y equals negative 0.05. And as we zoom out, that green line starts to look more and more curved. And if we zoom out far enough, we can actually tell that that green curve is the shape of a parabola. The equation of this green curve is actually y is equal to 0.25 x squared minus 0.05. Now that we've seen some examples of how a curve can appear to be linear if observed on a small enough scale, let's see how we can apply that. Linearization uses the equation of a tangent line at a point x equals a in order to approximate a y value near x equals a. And it's important to realize that the point that we're approximating needs to be near x equals a. If we're using a linear equation to approximate a curve at a point, the further we get away from that point, the worse our approximation will be. Here's an example of that. Let's consider that green curve from before. If we want to use linearization for this curve at x equals 0, we need to find the equation of the tangent line at x equals 0. That would be y equals negative 0.05. If we zoom in really close to 0 on a small scale, that blue or purple line is an excellent approximation for the green curve. However, if we zoom out far enough, we'll see that the linear approximation ends up being a terrible approximation of the actual value. If we do the linearization of the green curve at 0, and then want to approximate the value of the green curve at 2, we can notice that we're quite a bit off here. The vertical distance between these 2 points is equal to 1. At x equals 3, the vertical distance is even further away. And the further away from that original point where we did the linearization, which was x equals 0, the worse our approximation is. Let's look at a few quick examples of how to find the linearization of the curves we observed above. And remember what linearization really is. It's just the equation of the tangent line. Previously, when we wanted to find the equation of a tangent line, we just started with the point-slope equation of a line. Y minus y1 equals m, parentheses, x minus x1. In linearization, you'll be given some value of x. Think about the x value that you're given as x is equal to a, or if you prefer, that is just your x1. So that means that your x of 1 is equal to a, y of 1 would be f of a, and your slope is the slope of the tangent line, which is the derivative at a. That means the point-slope equation of a line is y minus f of a equals f prime of a, parentheses, x minus a. Let's find the linearization of that red curve on the left, y equals sine of x. And we'll do this at x is equal to 0. This value is 0. This is our x1 value. Or you can think of this as your a value. In order to find the linearization, we're going to use the point-slope formula, and we're going to have to substitute in for the values of a, f of a, and f prime of a. We know that a is just equal to 0, so that's an easy one to plug in. F of a would just be plugging 0 into our y equation. Sine of 0 is just equal to 0. So that means we can plug in a 0 for the f of a. Next, we need to find f prime of a. Well, in order to find f prime of a, we first need to find y prime. The derivative of sine is cosine. That is our f prime of x, and if we plug 0 into that, we'll have cosine of 0, which is equal to 1. So 1 goes in for the f prime of a. Let's simplify that equation and solve for y. That would give us y is equal to x. This is the linearization of sine of x at x equals a. Notice that y equals x is exactly what that red curve looked like when we zoomed in close enough. Next, let's find the linearization of y equals x cubed minus x. If we do everything right, it should be y equals negative x. Since we're finding the linearization, let's start with the point-slope formula. Y minus f of a equals f prime of a, x minus a. In this case, our a is equal to 0, so I'll replace all the a's with zeros. I need to find f of 0, so we substitute 0 into the y equation. 0 cubed minus 0 is equal to 0. So replace the f of 0 with a 0. Now we need to find f prime of 0. First, let's find y prime. The derivative of y would be 3x squared minus 1. That is our f prime of x. So all we need to do is substitute 0 into f prime. That would give us 3 times 0 squared minus 1, which is equal to negative 1. So replace f prime of 0 with negative 1. Finally, we can simplify this equation and just solve it for y. That would give us y is equal to negative x, which is exactly what that curve looked like when we zoomed in close enough. The green curve was y equals 0.25x squared minus 0.05. Let's start with the point-slope equation. A is just x equals 0, so replace all of your a's with zeros. We now need to calculate f of 0 and f prime of 0. F of 0 would be 0.25 times 0 squared minus 0.05. This is negative 0.05. We can replace f prime of 0 with negative 0.05. Y prime would be 0.5 times x. So then f prime of 0 would be 0.5 times 0, which is 0. So replace f prime of 0 with 0. If we simplify that equation and solve for y, we would find that y is equal to negative 0.05. This is the linearization of our original equation. We thought this looked like y equals negative 5, but it turned out to be y equals negative 0.05. Our original estimation for this green line was off only because we didn't know the scale. The y-intercept looked like it was y equals negative 5, but in reality it was y equals negative 0.05. So now that you have a pretty good idea of what linearization is and how to find the linearization of a line at a given point, in the next video we'll look at what we can do with this information. How can we apply the linearization at a point to approximate a value near that point?